So on Tuesday, we talked a lot about oxygen nucleophiles and how they interact with ketones and aldehydes. Today, we're going to look at nitrogen nucleophiles, and luckily the reactions are somewhat similar. So let's take a look at the overall reaction, and then we'll go into the mechanism after. So we can imagine that we've got an aldehyde or ketone. For this example, I'll just stick with aldehydes. And then what we're going to do is we're going to react it with an amine, and I'm just going to make this R group red so we can kind of keep track of things. Or sorry, green. Holy cow. Some days are better than others. It's an R. All right. And we've got acid around. We saw that we needed acid when we had alcohols around. The same's true with amines. However, I'm going to put an asterisk next to this and say we have to be super duper careful with the source of acid for this one. So the note is that you typically don't spike this with sulfuric acid. Does anybody know why? What's the problem if we have a lot of acid around? We do acid-base chemistry. What's the most basic site? The nitrogen. So if we have a really good acid around, we're going to protonate that nitrogen. It's going to become positively charged. Will it be a very good nucleophile at that point? No. So we have to be super duper careful about the acidic conditions. Instead, you normally run this in a buffer. So the pH of your buffer should be between 4 and 5 normally. If the pH drops too low, you shut down the reaction because all of your amine will be protonated. And if all of your amine is protonated, you won't have a good nucleophile anymore. All right, so the other thing to note is in this example, I'm using a primary amine. Meaning we've got one R group coming off of it, not two R groups. We will see a reaction that's similar with secondary amines, meaning two different R groups coming off of there. And in this reaction, you make a new molecule where you have a double bond and your R group's still coming off of the nitrogen, and you kick off water. This new functional group where we have a carbon-nitrogen double bond is called an imine. So we do need to remember that as a unique functional group. All right, so let's try to make sense of the mechanism. This mechanism is fairly similar, but a little bit different compared to the one with alcohols. So we'll start off with our aldehyde. And we've got our... It works with ketones as well. However, aldehydes typically are a lot more reactive, so you see a lot more imine formation with aldehydes than you necessarily would with a ketone. However, it works for both. And we'll stick with that same amine that we had before, and I'll color code it. And we've got our acid around. In this case, instead of protonating the carbonyl, we're going to have the nitrogen nucleophile attack directly in. We know that under these conditions, that carbonyl oxygen's not the most basic site around, so really not a lot of it's going to be protonated. And the nitrogen lone pair is a much better nucleophile than an oxygen lone pair. Why is nitrogen with a lone pair a better nucleophile than oxygen? Anybody remember? So nucleophile is giving electron density. Why is nitrogen more willing to give an electron? It's less electronegative, right? So its lone pairs are being held less tightly, so it's much stronger as a nucleophile and more willing to attack in. Yep?
So if acid base is the fastest reaction in chemistry, well, the pH is between 4 and 5, why does it
The reality is some of that amine will be protonated in solution, but that doesn't take you in a forward direction, kind of like we were talking about yesterday. So you can show that, it just doesn't really help you. Yeah. Okay, so now we have this nitrogen attacked in. We've got oxygen with a negative charge now, so slightly different intermediate than we've previously seen. All right, now the next step is typically that acid will protonate the oxygen, because that's pretty unstable under these conditions. We have this positively charged intermediate, right? And now what we're going to do is kind of like what we saw yesterday. We're going to move a proton around. Okay, so what we're going to do is we're going to move one of these protons coming off the nitrogen over to the alcohol. So I'm going to just shorthand this plus minus H plus. But typically the buffer or your solvent will facilitate the movement of these protons. Yep.
In that transition state, I'm seeing both a minus and a positive charge.
Yep.
Where we just came from an acid.
Yeah.
What's stabilizing the negative charge of the acid?
Yeah. So that's one of the infuriating things in chemistry is we tell you one thing and then we do another. So yesterday I told you under acidic conditions, avoid negatively charged intermediates. This is kind of a weird exception. Like we were saying, if it were acidic enough to protonate that oxygen, we would also be shutting down our amine. So really, this is what theory is showing to be the most probable mechanism. To be perfectly honest with you, we're not 100% sure. It's just the most likely and most reasonable. Does that make sense? Yeah. That's the weird thing in chemistry that used to drive me nuts, is you can prove a mechanism wrong, but you can't prove a mechanism right. Yeah, it's science in general, right? But as a student, oftentimes you just want the right answer. You don't want to know what the wrong answers are. You just want the right answer. But that's not really how it works. All right, so we get this proton moved over from that nitrogen to the alcohol. And now this nitrogen has a lone pair. Whoops. And this is a good leaving group. So this nitrogen lone pair can be shown as shoving off this water, or if you want, you can show water falling off, almost like an SN1 style reaction. But in either case, you're getting to the same intermediate. And we know that this intermediate is most likely, why? Why is this stable? Come on, you know the answer. Resonance, right? There we go. And then last but not least, water that got kicked off can deprotonate. And we can get to our final iminium ion, or sorry, imine, plus our conjugate acid. So I did want to clarify that this is an imine. This is the iminium ion. So they're closely related to one another. Some books will show it stopping at the iminium ion. Other books will show it stopping at the imine. In reality, it's going to be in equilibrium, right? Yep.
So if it's a like secondary or tertiary amine, is it still called amine, or is it?
No. So we'll talk about what occurs with secondary amines next. Tertiary amines typically are pretty crummy nucleophiles. Does anybody know why? Close. So imagine you're a tertiary amine, right? If you're a tertiary amine like this, you are so sterically bulky, you're going to be a super duper crummy nucleophile, right? So really you don't see these reactions with tertiary amines, but we'll look at the secondary amines ones next. All right. That's a good question. So normally you see this strictly done between a pH of 4 and 5. That's been experimentally shown to be the sweet spot for doing this reaction. You don't see it at a higher pH. Yeah. All right, so let's take a look at secondary amines. All right, so in this one, it's going to be the same idea, but now we've got two different R groups bonded to a nitrogen. And we've got, again, our pH-controlled conditions. Yep.
No matter if the R groups are, like, what those are.
Nope, they could be the same, they could be different. Usually they're the same, but not always.
I mean, like, if they're both, like, phenyl groups or something crazy, like, is that gonna,
Usually they're not phenyl groups. Why do you think they might not be phenyl groups? Because they're bulky and that lone pair on the nitrogen would be delocalized into the ring system, meaning it would be a pretty crummy nucleophile. So normally the R groups are aliphatic. As far as I know, usually that's the case. All right, and then when we do this, we actually get a different product than an imine. In fact, let me change this R group. I apologize. Let's change this to a CH3, just so we're consistent. People are all huffing at me like, how dare you? Is there no justice? All right. So instead of calling this an imine, this one's called an enamine. So we're starting out with the secondary amine in this case. Why do you think it's called an enamine? Yeah, it's got an alkene and an amine, so it makes a lot of sense, right? Just like we talked about enols, half alkene, half alcohol. This is the analog, right? So we've got an enamine here. And same sort of idea. Again, we want to buffer this at a pH of 4 to 5. All right, so let's try to figure out why we're making an enamine as opposed to an imine. And luckily, the mechanism is remarkably similar. Oops. Yeah. No, typically you'll just see, at least in the textbook, a proton with brackets around it, meaning it's acidic conditions, but acidic conditions is a super vague term, right? So in this case, we're trying to note that, yeah, it's acidic, but more specifically, it needs to be within this range. Yeah. All right, so the mechanism. We've got our aldehyde. We've got our secondary amine. Again, I'm just going to label these as red R groups. Ha, ha, ha. All right. And then it's going to attack in, pick up electrons. We know we don't want it too acidic or else it'll trap our amine. I'm going to confuse everyone on YouTube. Whoops. This guy has a weird sense of humor. All right. Yep. All right, so we've got this intermediate where the secondary amine has essentially attacked the electrophilic carbon on our aldehyde. And then in our next step, we're going to protonate the oxygen. That's going to occur very rapidly because we are under acidic conditions. Oops, let me keep it color-coded with red. There we go. All right, and then in the next one, we're going to, again, shuttle this proton from the nitrogen over to the alcohol group. So I'm just going to indicate this with plus minus H plus. So now our alcohol has 2 protons. Yeah.
So is that another reason why tertiary would work, because there's no nitrogen to shell?
That's part of it, although we are under acidic conditions. So there's always protons around to shuttle. other thing too, we'll talk about that in a second, is this next step and why it wouldn't work with the tertiary carbon. So just like we said before, this alcohol is a great leaving group because now it's protonated. So I should say this protonated alcohol is a good leaving group. This will kick off that alcohol. I'm funny. All right. I don't know. Humor me. All right. So now we've got this that looks a lot like an iminium ion, and we've got water floating around. Why wouldn't that step work with the tertiary alcohol? Yeah, we couldn't form a double bond, and we'd have an intermediate that's not resonance stabilized. So we just really don't observe this sort of mechanism occurring with the tertiary amine. All right, next step, though, is this is pretty unstable. And so I apologize, I'm going to change this slightly. I'm going to show each and every one of these hydrogens. All right, so it's relatively unstable. However, this water can grab any one of these protons and kick electron density all the way up to that nitrogen. This allows us to get rid of that positive charge on that nitrogen and finally end up with a neutral organic product. Where we now have a lone pair on that nitrogen, and we regenerate our acid. Does that make sense? So really its end goal for this reaction is to make a neutral product, which is why we don't end up with the carbon-nitrogen double bond, because you can never have a neutral product in that case. But in order to get an enamine, you must have a carbon with protons, right? If that carbon is tri-substituted, you're essentially stuck at that point. You have to have a proton over there. Yep.
So then people push it to the right, you have to just remove water as you go.
Yeah, so if we want to push the reaction towards the enamine or the imine, one simple trick is remove water from the reaction mixture. There's a ton of tricks for doing that. Like I said, there's glassware and distilling techniques for doing that. Another common one is there's these actual little beads called molecular sieves that you can put in, and they're designed to basically be little sponges for water. They'll only soak up water, but the pores are so small they won't soak up larger organic molecules. So sometimes you'll even see those in reaction conditions. Does that make sense? All right, so let's try a fill in the blank one. So we got this ketone. What ketone would this be? What's its name? You could call it ethyl ketone, although people might look at you a little funny. What's the IUPAC name? 3-pentanone, right? So this would be 3-pentanone. And we'll react this with diethylamine. And again, we're going to run this under buffered conditions. So I'm just going to write H plus with a little red asterisk so we remember it's not the same sort of acidic conditions as with alcohols. And my question is, what sort of box or what sort of products would we get in this box? I'll give you a hint. There's more than one product. Give me a thumbs up if you think you might know what the two different products are. I'm not ready yet. Did anybody watch Mad TV growing up? With Stewart?
Oh, God damn it. I purged that. Why?
All right, so let's really quickly try to break this apart. I'm not asking for a full mechanism, I'm just asking for the product. So looking at the amine, what sort of product are we going to get? Are we going to get an imine or an enamine? Enamine, all right, so we've got to get a double bond. All right, so one's pretty easy to spot. We could get a double bond right there. And then that position that used to be a CO double bond would be a nitrogen with two ethyl groups. So it would look like that, right? A lot of people would be tempted to put the double bond also on the right-hand side. Exact same thing, right? All right, so now the question is, well, what the heck is the second product? What do you think?
Would you get a 3-hexanol, just would it react with the first reagent to get like a byproduct by accident?
No, I'm looking for two different enamines here. Anybody else have an idea? What do you think? Not quite, because we always need essentially one of these protons, right? In order to kick up electrons to that nitrogen. Anybody else have an idea? Give you a hint. It's a lot like elimination chemistry. Right, we're making a double bond. What sort of alkene is this? Is it E or Z? Okay, so it's Z. What about getting the E alkene? Ah. All right, what's the relationship between these? Diastereomers. So under certain circumstances, you may have to worry about this, right? So always watch out for stereochemistry anytime you're doing these reactions. All right, let's do another one. All right. So let's do this one. We'll mix it up and go to a ketone. But now we've got a different nucleophile, right? All right, so same sort of idea as before. All right, now the question is, well, what in the heck would we make here? Well, let's think about this, right? We've got a nitrogen that could act as a nucleophile, and we also have an oxygen that could act as a nucleophile. Which one's more competitive as a nucleophile? Which one's holding on to its lone pairs less tightly? Nitrogen, which means its lone pairs are more available to act as a nucleophile, right? So that means that this nitrogen must be more nucleophilic. All right, second, do we think we're going to get an imine or an enamine? An imine, right? Because it's a primary amine, right? So now let's try to predict what the product would look like if we're making an imine. But give me a thumbs up if you think you got this one. If you, 8 more minutes, that's a long time. All right, so in imines, where do the double bonds go? Is it a carbon-carbon double bond or a carbon-nitrogen double bond? Carbon-nitrogen. So we can go ahead, plug that in. We're going to get an OH here. We're kind of purposely keeping the R groups vague at this point. And then our byproduct, we know it's going to be water for this reaction. So if you want to push the reaction forward, you just remove water from the reaction and take advantage of Le Chatelier's principle. All right, this is its own unique functional group. Oxamine. So it's a little bit different than an imine, but you might occasionally see this as well. Big take-home message is nitrogens are way more nucleophilic than oxygens, therefore the nitrogen is going to win out in this reaction. Yep?
So is the acid not catalytic?
The acid is catalytic, right? So that's why I have the H plus in brackets. For all of these reactions, the acid is catalytic, whether or not we're using alcohols or amines. The byproduct, though, is water, right? So we're kicking off water in this process. The water originally was this oxygen in the carbonyl. All right, there's another one. This is my favorite one. All right, so same idea, right? What are we going to get out of this one? An imine or an enamine? Enamine. Wait. An imine. Ah. All right. So it's remarkably similar, right? In this case, it doesn't matter. The nitrogens are equally nucleophilic. Our byproduct, in this case, is going to be water. Give you the exact same product. So the question is, can you add in another ketone and have this continue to react? Normally it'll stop here. Yeah. All right. So the starting reagent here is called hydrazine. This used to be used as a rocket fuel. And when you react it with a ketone or an aldehyde under the appropriate buffered conditions, you can make what's called a hydrazone. All right, so the cool thing with this, we'll talk about this next, is we can actually treat this with potassium hydroxide, water, and heat, meaning that hydrazone, once we isolate it, what you can do is go all the way to an alkane. Kind of cool chemistry here. So theoretically, we can start out with a ketone, go to a hydrazone, and end up all the way with an alkane. You guys want to see how that works? It's not magic. We will be tested on it. So yes, you would like to know how it works. All right. All right. So let's take a look at the overall one just to kind of reiterate what's going on in this. This is called the Wolff-Kishner reduction. All right. And just like I said before, you can have a ketone or an aldehyde, doesn't really matter. You treat it with hydrazine, and under the appropriate acidic conditions, if you remove water, you can make your imine, which is technically called a hydrazone. Whoop. And then, like I said, the reagents necessary to remove that imine, slide this over a bit. For KOH, potassium hydroxide, sodium hydroxide works too. For whatever reason, he tends to use KOH in the book. Water and heat. And when all is said and done, you end up with an alkane. What do you think the byproduct is in this last step, though? What would make the most sense? Well, we've accounted for all of our carbons. We can shuttle protons around kind of all we want using bases and acids. What would be super duper stable on its own? What makes up the majority of the air we breathe? Nitrogen, yes. So in this reaction, we make nitrogen gas as our byproduct. That's the key feature of this reaction. It is when you produce nitrogen gas, you're no longer under equilibrium control, right? When you produce it a gas, it bubbles out of solution and drives Le Chatelier's principle for you, which is kind of neat here. So let's take a look at the overall mechanism. All right, and I'm going to jump straight to the hydrazone because we've already done a fair amount with imines. And let me actually show these bonds because we know we're going to have to move protons around. All right, so I'm going to show the protons coming off of the terminal amine there. And we've got hydroxide floating around. I kind of gave it away. But those protons coming off the terminal end are going to be most acidic. Why? Resonance. It's like people are seeing the trend here. All right, so we can pluck that off. In particular, the main thing that happens is this will cascade down over here, and then cascade down to that final carbon. I have seen it before, though, where you see the negative charge on the nitrogen as an intermediate and then clamps down. The reality is the resonance structures, right? So whether or not you show the negative charge on the nitrogen or on the carbon doesn't really matter, right? They're both appropriate. All right, so in this next step, though, we have carbon with the negative charge. All right, like I said, that negative charge could be delocalized over here. But what happens if there's an acid source around? And we protonate that nitrogen? We essentially just go back to our starting material, right? So it doesn't make a whole lot of sense, which means that the most important representation for the resonance structure is with the negative charge on that carbon. All right, so now we've got our conjugate acid, water, floating around. And we know that carbons with a negative charge are ridiculously unstable. So it'll quickly steal this proton back. All right, and now we have hydroxide floating around. It can do this one more time. So just like we saw before, most acidic proton would be right here. And in this next step, we're going to make a nitrogen-nitrogen triple bond, which is pretty cool. And then kick electrons down to the carbon. But the key thing is that this is a gas. Really, the first few steps we could have shown with equilibrium arrows, but once it reaches this point and liberates nitrogen, it's no longer under equilibrium conditions, which means the whole equilibrium is no longer under equilibrium conditions. All right? And then in the very last step, we can pluck off a proton from water and we can get to our cyclohexane. All right, so if we think about this, we've seen another reaction that was pretty dang similar where we got rid of a carbonyl group. Who remembers that one? Oh. So let's recall. Remember this? Does anybody remember the reagents we need? Zinc, mercury, and HCl, right? This is the Clemenson reduction. All right. Cool thing is you can do this a different way. That's a good question. The question was, why would you do that? This is much harder to write out. Why would we maybe choose the bottom one and not the top one? We avoid working with mercury. So in a way, this is a much greener reaction. However, it's not perfect. I already listed one of the downsides is that it requires the use of rocket fuel, which is inherently less than safe. The other problem that I see with this one is we're using pretty strong base, where up here we were using acid. So really the Wolff-Kishner reduction can only be used if you don't have things that are base sensitive, right? If you've got a base sensitive functional group, you really don't want to use the Wolff-Kishner reduction. On the flip hand side, the Clemenson reduction, the one on the top, really only works for aromatic ketones, meaning one half of the ketone is attached to an aromatic group. It doesn't work with aliphatic ketones, meaning no aromatic rings, where the Wolff-Kishner reduction doesn't care. It'll work on just about anything. Yeah?
I was going to ask what aliphatic means.
Yeah, aliphatic just means alkane, right? So no aromatic groups, nothing like that. Yep, good questions. All right, let's do a few more practice problems and then we'll call it quits. All right, so it's almost like you'll need to know this for synthesis, though. All right. So how in the heck can we make this molecule?
Well, that's Jeff. Jeff, how do we make a molecule?
I would hire an organic chemist to tell me how to make it.
If I had to guess, probably nitrogen, biphenyl,
All right. So now let's stop and look at these, right? So first one, working backwards. Is it an imine or an enamine? Enamine. All right. Not too bad. All right. So now what I like to do is identify the carbon that used to be a CO double bond, right? So where is the carbon that used to be the carbon that was the CO double bond carbon?
One attached to the nitrogen on the left, it's the top.
Okay, so this one used to be the CO double bond position, right? Yeah. All right. So working backwards, we can say, well, that means that this portion must have been what? It must have been the position with the CO double bond. Was it a ketone or an aldehyde? Ketone. So that's not too bad, right? So we can go ahead and we can say, well, that position must have been a ketone, where that red carbon we've kind of matched up, right? Not too bad. All right, and then down here, we've got this other chunk. That must have been our amine, right? In this case, it's an enamine, so it must have been a secondary amine, right? So now we can go ahead and we can say, was like this. And then what other reaction conditions do we need in order to couple these together?
Catalytic acid between 4 and 5.
Okay, so we need catalytic acid. So I'll just put my H plus with my red little asterisks. And then in order to get this out of equilibrium conditions, we need to remove water. So I'm just going to write minus H2O, and voila, right? This looks super complicated, but if you work backwards slowly, it's really not that bad, right? So let's do the same thing with the next one. All right, next one. Is this an enamine or an imine? Enamine. All right. So now let's think about this one. Where must the carbon have been that was formerly a CO double bond carbon? Yeah, essentially the same spot, right? All right. So now when we think about it, we could say, well, this part over here must have been a ketone, right? Just kind of like we did before. And then this part must have been an imine, but what do you notice is different about this? It must have been connected to begin with, right? So these weren't two separate molecules to begin with, because at this point, they're stuck together. Not too bad, though. Okay, so now let's go ahead and do that. So I'll go ahead and label this red carbon. And then down here, we've got a methyl group kind of hanging out. And then I'll do the other piece right here, and then I'll try to circle that green chunk. So we've got 1, 2, 3 carbons. And like I said, there's this attachment point right there. So you can actually have these occur via an intramolecular reaction. Make sense? A little bit tricky. Want to try one last one? I think we got barely enough time. So we got H plus minus H2O. Ah. All right, so one super duper last one, just to finish practicing. All right, is this an imine or an enamine? It's an imine, right? So a little bit different this time. Where must the carbon have been that used to be the CO double bond carbon? On the double bond. All right, so that makes sense. So now what we can do is just like before, we can circle one part and we could say, aha, that must have been the ketone. And then over here, we can circle that part and say, well, that must have been our amine. So over here, we can say, whoops, let me color code it appropriately. Got the CO double bond. We've identified our red carbon. Over here, just like before, our ketone must have been linked to our amine. So I'll draw that with a black carbon-carbon bond. And then we've got 3 carbons coming off. So 1, 2, 3. And just like over here, we said that that was the connection point. Main difference with this one versus the one right above it is we have a primary amine, not a secondary amine. Therefore, we're getting our double bond in a different position. So like I said, don't let these intimidate you. I've seen this pretty frequently where on the first exam, people look at these and they're like, oh my goodness, I don't even know where to begin. What is this voodoo? Just break it down into the easy parts, identify whether or not it's imine, enamine, identify where your CO double bond used to be, and then piece it together. Yep.
So, if that bottom on the if the bottom methyl group exists, the double bond there instead of the top one, because it's more stable.
Yeah, so for the top one, there would likely be a mixture of different products. We were just trying to work backwards retrosynthetically. That's a good question, though.